here's what we're going to do. Chapter 6, last section. So we've started to understand this concept of a distribution. And so last class that we spent on z-scores, we talked about how to use the chart and how we can take that z-score and the area under it and treat it like other things. Today we're going to start treating that area under the curve like probability. And just a little refresher on probability theory. The probability of an outcome or an event is simply the representation of the number of ways in which that outcome can occur divided by all of the possible outcomes. So it's a fraction, and as a number, probability can never be higher than 0. Because you can't have more ways an outcome can occur than possible outcomes. So it's always going to be 0, or excuse me, at most 1. And the minimum is always 0. Because if an event can't happen, you get a 0 in your numerator. No matter how many possible ways an outcome can happen, you're going to have 0. So probability is just by definition, by logic, bounded between 1 and 0. So if we were to represent something like a dice, what's the probability of rolling a 2? It's 1/6. The number of ways in which that outcome can occur. How many ways can you get 2 on a 6-sided die? One way, the 2. How many possible outcomes are there? 6, because there's 6 sides. Okay. If you want to know whether or not dice are fair dice or not, look at them and see what number is on the opposite side. So if I have a 1 on one side, what should be the number on the opposite side? Why? But why? Why do I want to know if this is a fair die or not? So if I have a 3, what should the number be on the opposite side? What does 3 plus 4 and 6 plus 1 have in common? So each dice has 7 dots removed from it on each side, on each lay. Some bitch. What do you know? All right. So a die should always be like that. So if you're looking at a 1, the 6 should be on the bottom. Okay. Just a thing. All right. Speaking of dice, anybody here play craps or know the game of craps, the one at the Vegas casinos where you throw the dice? You know what the bad number in craps is? The number you don't want to roll? It's a 7. Why does that make sense for 2 dice to have 7 be the bad roll? Because 7 is the what outcome? Nope. It'd be the most likely outcome, right? We would expect to roll a 7 because it has the most frequent pairings. That's the other part about probability that's nice, is that you can add probabilities up. So probability is additive. They all add up to 1, and when we combine potential outcomes, like rolling a 1 and a 6 and a 2 and a 2 and a 5, a 3 and a 4 and a 3, a 5 and a 2, and a 6 and a 1. We take all of those probabilities and add them together. 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. Actually, it's 2 dice, so it's actually more than that. Sorry, we gotta get into 36ths. But again, let's not let the actual math distract you. Right? This is the most frequent probable outcome. I'm in the wrong file because my little table that showed that being right isn't there. So why aren't I? Okay. You just have to trust me on that. I did a table, but the table's not there. All right. Why do we need to understand probability better? Well, because of what we're doing. As social scientists, we're using samples a lot. And we're trying to draw conclusions about populations based upon our tiny little samples. With each drawing of a sample, what we're really doing is, and this is how I want you to think about it, we're plucking from that larger population. And for me, whenever I think about this, right, if I've got a normal curve, and in nature I think that the normal curve is the best representation, then there's a true value out there, mu, a true value out there that best represents that type of data. Again, it could be shoe size. And when I take a sample, I am creating statistics from that sample. Something like my X bar. So back when I taught this class daily, not in a hybrid fashion, the way that I would drive this home is I'd give everybody a pair of dice. Now mathematically, we know the distribution of rolling 2 die. What's the hardest outcome to get? Because it only occurs one way. 2 and 12. It is hardest to get 2 and 12. It is 1/36th. That's the probability of getting 2 and 12. Because only one outcome out of 36 possible pairs, actually 2 out of 36, because you get 1 and 1, is the potential outcome. So rolling a dice has a known distribution. If you roll 2 dice, and that's the table, like I actually had that. I don't know where it went, disappeared. I had it. I could show you what is the probability of an outcome of rolling a 2, a 3, a 4, a 5, a 6, 7. 7's the middle, it's the highest one. 8, 9, 10, 11, 12. And it sort of goes down from there. That is a known distribution. So what I would do is I'd give everybody a pair of dice, and we know that the average roll should be 7. First, you need to learn how to roll dice on the table. 2 and a 6, 8. So I'd have everybody roll their dice 10 times and then compute their average. And then we'd get somewhere close, but not quite 7 when we added everybody's up. The more as our sample size gets bigger and we have a better sample, our mean will get closer and closer to 7. There's some probability simulators online where you can like keep hitting the button and do a number of trials. I might get to that at some point this semester. And one time we did like 10,000 dice rolls. And we watched how it moved closer and closer and closer to the actual probability. This idea that our samples are really, when you think about them, random draws from a distribution, it brings into it a little bit of error, a little bit of sampling error. And we'll account for that later in the semester when we start doing tests of sample means compared to population means. But I just want to sort of introduce this now, this idea that because we're working with a sample, we can't forget that when we use probability. like I said, we'll come back to this. So when we say we're talking about a normal curve, we're talking about something like z-scores, not only is that z-score representing the value in the distribution, it's also giving us area under the curve, but area is also probability. This makes me really wish I had that. Hold on a second. I got one more idea to get that table back. Yes, open it up. Looks like crap now, but I got it. Nah, that's not the one I wanted. Oh, there it is. It's in that page. Oh, it was there the whole time. Okay. Oh, because it was a different example. This isn't quite the same distribution, but I borrowed it. So don't pay attention to the numbers, just pay attention to the shape. This is actually a binomial distribution where you have 2 outcomes. This has 6 outcomes. This is not quite the same, but the shape of the curve was the same. So I borrowed it. So as we can see here, our average outcome, which should be here in the middle, right? Highest one symmetrical on both sides. What we're actually doing when we're rolling the dice is we're sort of like picking in and grabbing one outcome, right? So I roll the dice, I got a 10. I reached into this distribution and pulled out a 10. Well, there's not a lot of 10s in this distribution. It's kind of rare, right? There aren't a lot of them in there. But that also represents area. It represents percentages. Because when we find what is the area of the curve between 2 points, that's telling us what's the probability that we're actually getting a number in between those 2 points. Oh, yes, I got Jeff. Jeff understands. Does that make sense to you? So again, what is the most frequent outcome when you roll a pair of dice? 7. So there should be a lot more 7s in the randomness than there are 2s. Because there's not too many of those, really small number. Okay? So again, if we think about this in terms of area, that 7 column is the biggest column. There's lots of 7s in that distribution. Do I have everybody? Do I have you? You sure? Hampton? All right, good. So essentially, I know you would never do this, but the percentage of scores between 2 z-scores is the exact same thing as the probability if you were randomly selecting z-scores, because you know we do that for fun on Friday nights. Tell me a z-score between -3 and +3. I don't know, like 2.75. It's the same thing. Again, nothing like math and statistics to tell you about, well, if you did randomly do this thing that you would never ever do in your life, it would actually be the same number. Magic. Poof. Yeah. Just have to go with me on this one. All right. Now, I have a problem with this textbook. And I didn't really notice it last year, because when I was doing Chapter 6 last year, we had that hurricane thing, and I had to cancel class that week, and so I just put something up online to make up for it. But now that we're here and in person, I'm a little mad at Howard, because Howard's making my job just a little bit harder. Because I have been, for the last 3 weeks, trying to teach you this thing called a normal distribution. And what does Howard do in chapter 6? Introduces a new one. One that, quite frankly, you don't really need to know. It's called the binomial distribution. A binomial distribution is when you have a situation where you only have 2 outcomes, by 2, and those 2 outcomes could be anything. It could be like a light switch, lights on, lights off. It could be gender. Could be, did you get the question right or wrong? No partial credit. Or it could be the flip of a coin. Only 2 outcomes on the flip of a coin, heads or tails. Don't tell me about landing on its side, never happens. That's why we put ridges on a quarter. Actually, I just made that up, but it makes perfect sense. This is a binomial distribution. It comes from a really, really ugly looking equation. And the equation for this one wants to know how many trials there are. It has the funkiest math that you could find in this class, and I'm not going to show it to you. Because it's not just add, subtract, multiply, divide. There's another thing. It's like 2 parentheses and a couple of numbers, and it involves that exclamation point thing. Yeah, we don't need to go there. When your mathematical operators are forms of punctuation, we're just going to take a time out on that. So I'm not going to require you to do this. I'm not even going to show it to you. It's scary looking. But let's just remember that with a flip of a coin, the more times we flip that coin, our average value should be what? Should be 50-50, right? So if we were going to do this in terms of probability, it would be what number? 1 and 2, which as a number is 0.5. Okay? So our expected value of a binomial distribution is 0.5. But as we get more and more events, the binomial distribution actually becomes normal. So what does that mean? Well, if you only flip a coin once, you don't really have a normal distribution because you have 2 bars, number of heads 0 and 1. But if I flip a coin a dozen times and then say, well, how many heads did I get? This is what the distribution looks like. I should flip a coin 12 times, I should get how many heads? 6, right? 50-50 shot. So what the shape of the distribution is influenced by is first the expected value, which we know already is half, if it's true, if it's a true coin. But what if it's a fake coin? What if it's one of those ones that has like extra head on it? Well, remember the dots thing? You totally understood the dots thing a second ago, right? The idea if you split it in half, it should have equal weight on both sides, right? What if George Washington has a little extra forehead on your quarter? It would weigh it towards that side. No, not that. There you go. He's got like an 8 head. You flip that coin, it's going to always land on tails because George Washington's heads will weigh it down. Gravity. Okay. So we can actually account for that too in that big, messy, scary equation that I'm not going to show you because the math is even hard for me. I have to look it up before I even attempt to do it. Again, parentheses are not a mathematical notation. Add, subtract, multiply, divide. So this is what it looks like. That's looking normalish to me, right? Why does it look normal? Well, let's think about the characteristics of a normal distribution. What does this have? It has symmetry. That's a good thing. What else does it have? It's unimodal. Anything else? Hey, those are the big ones. I'll be happy with those. Theoretically, the mean, median, and the mode would all be in the middle. Yep. That just tells us it's symmetric. All right. Let's go with that. So it looks very, very normal. So why would Howard do this to us? Why would he confuse us? What I really don't like is that in his example, to teach you what is, to me, the most important concept of the course, outside of the math, in the chapter, he uses whether or not you win a football game. Howard, the book is about social behavior. And now we're back to betting on football games. Like, no offense, but that's something that the math department would do. Like the probability of making a free throw. They're all degenerate gamblers over there. All right, I'm trying to explain human behavior, and you're talking about the relationship between the coin flip and whether or not you win the football game. Howard, come on, brother. What are you doing? So I'll walk you through it. I don't like it. I disagree with it. I will write him a strongly worded email someday. Today's not that day. All right. What he is trying to introduce to you is the concept of testing a research hypothesis. And his example in chapter 6 is the hypothesis that when football teams win the coin toss, they are more likely to win the game. Beats me. I watch a lot of football, and there's really no reason behind it, other than the coin toss gives you one and only one strategic advantage. Whether or not you receive the ball at the beginning of the game or you receive the ball at halftime. That is the only strategic advantage of winning the coin toss. And you lose the advantage of determining which direction you're going to kick, because the losing side gets to do that. But whatever. Okay, Harold, Howard, your book. We'll use your example. So that's a theory. He can construct a research hypothesis. And that's what we do as social scientists. We construct and then test research hypotheses. So what is his research hypothesis? Well, his theory is that winning the coin toss helps you win the football game. What would a statistical hypothesis look like? Well, a statistical hypothesis would say, how are we going to express that? In a 12-game sample, a football team that wins the coin toss should be expected to win an above average number of football games. And what is the average or expected outcome in a binomial distribution? Half. So in a 12-game sample, how many games is a team expected to win? 6. Does the team that wins the coin toss win more than 6 games? Why can't we be talking about something else? There you go. Is there such a thing as home field advantage? That actually makes sense, right? Not having to travel, having the fans get really loud when the other team's on offense. Yeah. Yep. Like that actually makes sense. But again, that has nothing to do with social science or human behavior, which is in the title of the book. See? Social and behavioral scientists. not how to bet a 3-team parlay. Like, come on. All right. So this is our introduction to probably what I think is the most important concept in the class, and that's hypothesis testing. Now remember, social science, we're fake science, so we got to make it look real science. So we follow a set of procedures. That makes us sciencey, right? A scientific method. I'm waiting for you to copy the slide. Go ahead. Even though they're all online already, and actually from your textbook. I got really lazy this week. I just used this complete presentation. So the first thing we do, we have to state the null and the alternative hypotheses, which means we have to know what a null hypothesis is. Then after that, we're going to do something to make a decision about the null hypothesis. That's where the math comes in. Then we're going to draw a conclusion from our analysis, our conclusion about the bigger concept, coin tosses in football games. I wonder if you can bet. I wonder if books close, sports books close after the coin toss. Maybe there is an opportunity to make some money here. Let's play this out. And then finally relate the result of the analysis to our larger research hypothesis. Look, steps. We have a routine. We're science now. I'm waiting. I'm being nice. Ooh, that was harsh. Okay. That's okay. I was in a pissy mood on Tuesday. I feel sorry for those guys. Can we move along now? Thank you. So let's start with the first little block there. What is a null and a research hypothesis, or an alternative hypothesis? Well, what we really need to do is set up an explanation of two outcomes. The first outcome, the null hypothesis, is always the one we actually test. And the one we actually test says there's no relationship at all. The null hypothesis proposes that the difference, change, what we observe in our data should show no relationship. So back to this football coin toss. I can't even say it correctly. The football coin toss example. No sense. In 12 games, the expectation is that the coin toss winning team would win 6 games if there's no relationship, because that would mean they have 50-50 shot at winning the game, and the fact that the coin toss had no impact whatsoever. Yeah, makes sense. So that's the null hypothesis. This is the one that we're going to test. The alternative hypothesis this is where we say that there is a relationship that exists. So, if there is a relationship between the coin toss and winning a football game, then we should expect in a 12-game sample that the coin toss winning team will win not 6 games. Now, what do we really expect them to do? No. If there is an advantage, sorry. We're back to alternative land here. Win more than 6, right? You can have multiple alternative hypotheses. Okay, alligator eats the bigger one. Win more than 6. Yeah. And less than 6. Or vice versa. I really don't know. You point to the little one. That is...
It's less than and greater than.
Yeah, less than and greater than. Just took me a minute. I got there. You laugh at my alligator thing, but that's actually how they teach first graders. All right? Because it's a lot better than saying you pick on the little one by pointing at, like that's how I remember it. But with Abby, we learned that it's the alligator wants the bigger meal. And you do have to do this too. Being a dad is fun. All right. So you can have multiple alternative hypotheses, but this is a professor move. Okay? This is what I'm allowed to do. You guys right now, you're just expected to know what a null hypothesis is and test it relative to an alternative hypothesis. So let's keep it simple for you guys. Because these alternative hypotheses are actually saying three different things. This is saying that there is an effect, right? That you're going to win not 6 games. This is saying it's a bad effect. See, what happens is you win the coin toss, and you're like, yeah, we're winners. And then you get overconfident, and then you get your ass kicked. Because you thought the coin toss was the important thing. That's a theory. Overconfidence of the coin toss. I can write a whole paper on that. I could easily do that. Do the same thing with the null hypothesis, or the third hypothesis, that actually you are going to win more than 6 games, right? Because it gives you confidence, and you're a winner already. You beat the team in a random flip of a coin. You're going to go out there and kick their ass. Sure. These are more academic moves. You're not there yet. The next thing you need to do is understand, make a decision about the null hypothesis. Well, you're not truly making a decision about the null hypothesis. You're actually making a decision about the conditions in which you would say the null hypothesis is wrong. That is known as rejecting the null hypothesis. That's what you want to do. You want to reject the idea that there is no relationship, because then you get to say that there is a relationship. What's the opposite of reject? No. Do not reject. If you ever accept a null hypothesis, I will disown you. I will not know who you are. I will deny ever teaching you anything. You'll be dead to me. You never, ever, 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 under any conditions, accept the null hypothesis. Because you only have a sample. You only have one draw from the population. What if you get a bad draw? Right? So you never accept the null hypothesis. If you want to, you want to show some shame, you can say, I failed to reject the null hypothesis. Because you have failed. But you never, ever accept the null hypothesis. That's not your call to make. So we have to say, all right, when are we going to reject the null hypothesis? Well, that's when we need to be sure that our sample statistic is a rare outcome. How do we know if it's a rare outcome? It has a low probability of occurring when the null hypothesis is actually true. There's a specific type of error we're trying to avoid here. And I'm going to borrow from medicine. You can make, when somebody comes in for a diagnosis, there's actually 2 types of errors that you can make. One is known as a false negative. That's when you say that the condition that they don't have. The other one is a false positive, when you say they have a condition and they don't actually have it. We have these two potential negative outcomes, right? Because what is the negative outcome of telling somebody that they're not pregnant when they actually are? What bad could happen? Yeah, they could go out and get really, really high, get their baby addicted, right? Not take their prenatal vitamins. Yay, drinking, right? Fetal alcohol syndrome. So there's a whole set of things that would be bad, right? So in those situations, we want to, err on the side of caution. You've heard that expression before, right? But let's just be clear. Those are things you really shouldn't be doing anyways. Like, baby or not, you shouldn't go out and drink a lot and get high. It doesn't hurt your baby, it hurts your brain. So I'm a little safe there. But what we really don't want to do is have a false positive. And I'm going to get away from the pregnancy example. Imagine if Alex came to my office and I said, Alex, sorry, buddy, I got some bad news. You've got like 4 days to live. Now, is Alex going to go out and do stuff that's like, taking his prenatal vitamins and eating clean and healthy?
I'm not going to take prenatal vitamins.
No. So if you got 4 days to live, what are you going to do? You're going to go out and drink and get high, right? And that's a scenario in which, again, we don't want to harm him. We don't want to give him bad news and then him go out and make some really stupid decisions. So we have these two types of error. And unfortunately, the way statistics works, if you increase one, you decrease the other. So if we decrease our chance of a false positive, we're increasing our chance of a false negative. In this world, which is better? Is it better to reject the null hypothesis and say that there's a relationship where one does not exist, or is it better to not reject the null hypothesis and say we don't know if there's a relationship? Yeah. All right. So that's better, so that should have a higher probability of happening. So we need to focus on the low probability being the bad thing, saying there is a relationship where one doesn't exist. Let's see if some heads can nod. You got that? We never reject. Yeah. We want to make it hard to reject the null hypothesis. Right? We want to make it hard to have a false positive because we don't want Alex going out there doing crazy things. It's actually a really good example. They keep trying to make like movies and TV shows based upon this thing. Like somebody gets a diagnosis that they're going to die, and then they actually live. That was a bad CW show a couple of years ago. Like, how would your life be different if you thought you were going to die? And then you live your life like you're going to die, and you tell people what you think of them, and you don't die. And you have to live with the sort of repercussions of that you thought you wouldn't have to deal with because you thought you'd be dead. Oopsies. There's also a bunch of movies, too. They're never really all that funny. Like Queen Latifah did one. She fell in love. And she's like, oh, it sucks. I'm going to die. And it's like, oh, actually, you're going to live. Oops. All right. So what do? We pick a low probability. In the social sciences, we've pretty much agreed 5%. 0.05. We want to make it really, really hard to reject that null hypothesis. Another way of saying this that's actually statistically wrong, but I'll say it anyways. So we want to have 95% confidence, even though this confidence and the confidence you feel aren't the exact same thing. But you'll appreciate that. The value at which we set our decision rule is called a critical value, and we also call it alpha. Don't know why. The false negative, that's called beta, which is confusing because there are statistics called betas, but Again, I didn't make any of this up. I'm just teaching it to you. So we want to keep that probability low. So we want to make it hard to say things like, if you drink red wine, you'll live forever. Or chocolate. Which one is it? Like dark chocolate's good? Red wine's good for your heart. Dark chocolate will make you live forever. Just waiting for the one about movie popcorn and nachos. Putting fruit in your beer reduces the chances of scurvy. Scurvy's a disease you get when you don't eat fruit. Pirates had it. That's why we have rum drinks. You'll figure it out later. All right. So 0.05. That's our number. So let's go back to this distribution that you know nothing about until about 40 minutes ago and use it on our example that is neither social or human behavior and work it out. So this here is our distribution. It's a binomial distribution with 12 events. And we know we've got 5%. Where should we put that 5%? I got a 100% curve. Where do I put the 5%? There, that'll make you feel better. It's a curve again. This is what we do. We take the 5%. The first thing we do is we cut it in half. Why should we cut that 5% in half? Because it's what?
It's the does not equal.
So where could it be?
It has to be between. I don't know how to explain it. But it has to be between, doesn't it?
Sort of. So you're right. We're saying it doesn't equal, so it could be more than or less than, right? Could be positive or negative. So I got my 5%, and I'm going to split it in half because my curve has two tails. And now where am I going to put that 5%? I just told you. I'm going to put it in the tails. Why? Because that's where the most extreme outcomes are. Now for this example, how do I know what the requisite number of games to win or lose is to say that there's a relationship with the coin toss and the outcome of the game? This is what I have to do. I have to add up these tiny numbers here until I reach 0.025. Because area is also the other one. The area is also the percent, and it's also the, starts with P, probability. And I want 5% of my probability. I put it in the tails. Split it in half. Okay. So how much area? Let's start with 12 wins. 0.0002. 11 wins is 0.0029. Do I have a lot of probability yet? No. What's 10? 0.0161. Now if I add all of these up, I have 2 plus 9 plus 1, that's 12. Carry the 1. 3 and 6 is 9. No 1 to carry. I'm getting close, right? If I'm looking for 0.0250 and I've got 0.0192, I'm almost there. But what happens when I add in the next one? I go over. So that's too much. I can't use that number. It's symmetrical. Nah, that's better. It's symmetrical, so I do it on both sides. Okay, let's translate this into something that makes sense. According to the binomial distribution, I have to win 10 or more games to reject the null hypothesis that the coin toss has no evidence. No influence of winning the coin toss. So this is the condition under which you win the coin toss and win the game. That makes sense. It shouldn't, but it does. Right? Because this is what's happening. Remember, in our 12 games that we look at, how many football games are played in a year?
What level?
Exactly. Let's just look at the levels where they do a coin toss. So how many levels do they do a coin toss?
NFL, college, and high school.
Yeah. So let me, let's reframe that question. How many football games are there a year? A lot. All right, we might even verge into what I like to call my favorite form of measurement, known as a shit ton. How much is a shit ton? More than a lot.
Too many.
All right, it's too many. All right, that's too many to really grasp our minds around, right? It's not quite that many. You've been in the military. All right, that's a different field of measurement. All right. That involves like cargo planes and stuff. All right. But there's a lot, right? There's a lot of football games. How big is our sample? Give me an exact number. 12. All right, we've looked at 12 football games. In his book, he looks at like, I don't know, the first 12 Super Bowls or something. That's a really small sample. So we got to be sure that the number of wins that we observe isn't plucked from what we would expect it to be. Because this number is not evenly distributed, right? It should be really rare to win 12 football games after winning 12 coin tosses. It should be really rare, right? And that's why we have this, and it should be really rare. Listen, if you win the coin toss 12 times and you are a football team, you should at least win a game or two. Unless you're the Browns. Even the Browns win a game. But I don't know how good they are at the coin toss, though, right? Jeff?
So, but like if you win the coin toss 12 times and you win the games 12 times, wouldn't it be like a strong correlation?
Yes, it would be, because that's really freaking rare. But we're not talking about correlation, right? We're talking about, let's take our sample statistic, which is number of games 1 out of 12, versus the expected value in a binomial distribution where you only have 2 possible outcomes in 12 trials. The expected value is 6. Because let's be frank, we expect football teams to win about half the time. And the good teams that win more than half the time are usually rewarded with what? And the teams that lose more than half the time are rewarded with what? Ta-da! Okay? So this outcome should be rare. And that's what we are seeing, that in fact it is rare. Make sense now? Okay. Again, just flip a coin 12 times. Tell me, do you think it's rare that you're going to get 10 heads out of 12 coin flips? No, because your expectation is that you only get 6.
So you're rejecting it because it's rare.
Because your sample is rare. Mm-hmm. There you go.
Big shake.
Okay, we're getting there. Again, this is not the best example. So as we start learning more methods of actually using this, it'll make more sense. Okay? Let me see what else I have to do, because I know I got like 5 minutes left. We talked about the decision rule. Oh, I want to do one more thing. Anybody have their curve? Their normal curve? You got one right there. So remember, what was our number that we put in each side of the tails? So how would you find the z-score that represents 0.025? Well, you look it up in the field. I don't need to look it up. It's a magic number to me. It's like pi. Pi is 3.14. For a z-score, it is 1.96. You verify that?
Yeah.
Yeah. That's just a number you will just memorize. 1.96. So if we're doing a z-score to see, again, is our sample statistic that we have really far away from the expected value, which is in the middle, the z-score has to be greater than plus or minus 1.96. Which, if you remember your empirical rule, 90-something% of observations are 2 standard deviations away. So it happens to work out that way for us. We talked about decision rule, draw a conclusion. Yeah, this is, yeah. Okay, last thing. We got to be really careful here. Now, we're not dealing with whether or not Alex has cancer or not. But what we are dealing with is how humans behave. And so one of the things that we really, really try to avoid is saying that we've proven anything. Our statistics are based upon probability. So what would one way be to prove that these dice are fair? Well, fair dice behave in a certain way, and that the expected outcome of rolling 2 dice is what? 7. So can I prove that these dice are fair by rolling them 1,000,000 times? No. What's really the only way that I can prove to you that these are fair dice? Nope. Because I can just paint the dots on there. I don't actually have to scoop the dots out. I can. I'm making a representation that these dice are equally weighted on each side. So how can I prove that they have equal weights on each side? Weigh them. That's the only way to prove that dice are equally weighted, that the weight is evenly distributed. I have to weigh the dice. Actually, it's called balancing. It's not weighting. I have to balance the dice on each side. This is not an unknown thing. We drive around on things that are balanced and proven to be balanced. They're called tires. That's why you have little weights attached to your rims. Okay? I can't prove something just by a sample. I can't, right? I can show you that they turn out to be behaving the way that fair dice would behave, but I'm not actually proving anything, right? It all has to do with a little bit of, let's say, luck. Or, if you want a fancy college word for luck is known as, stochasticity. Something is stochastic, it means it's random. So things happen to you in life are stochastic because they randomly happen, which is whether or not you have luck. Okay? So when you're writing about this and reading about this, you'll notice that we use words like probability and likelihood, but we're never actually proving anything. That's why we don't accept a hypothesis, or at least the null hypothesis. You never accept the null hypothesis. You can find evidence for your alternative hypothesis by rejecting the null, but you never prove anything. It's highly likely. Right? You can increase the probability of an event, but you can't prove it. You can't make something happen. I can't make a football team win because of the coin toss. All right, midterm next week. Look at your study guides, come to office hours, academic coaching. Finish up your exercises.